exercise for, the topics for the next 2 weeks. Bye-bye. Okay. Now, I actually gave you in your notes a couple of images that I'd had before, and it was just to remind you that water is a really important issue, and it's not just flooding. It's water quality, it's water supply, and it's a problem that affects us globally, and it's a problem that particularly impacts the lesser developed countries, but we're finding even in the United States, water supply issues are becoming important. So I'm going to focus on water supply and quality with respect to groundwater. And as I had mentioned earlier with surface water, there's a variety of ways, or rather uses for water, everything from public supply to thermoelectric power. And the colors, the brownish colors, are the percentages that are used for groundwater. Okay, and groundwater basically is not used for thermoelectric, but it is the dominant for irrigation and or for livestock rather than a variety of other things. Irrigation for total withdrawals, for the most recent data I can find, is actually the dominant use. Okay, we use more water, better said, more groundwater for irrigation than anything else. And one of the reasons you'll see that's important is because irrigation is the most inefficient way of using groundwater because of the high rates of evaporation and evaporative losses. So we'll come back to that. Okay. Now, this particular number here in red is what we call the percent consumptive use. And what that means is how much of that water is consumed for each given use. Okay, and we're going to focus on the use excluding thermoelectric. Okay, the problem is with irrigation, so much is evaporates. In fact, almost 2/3 of the water that's used for irrigation evaporates. So we call that a consumptive water use. Now, actually, it's not consumed in the sense of it's gone, it's up there, but it's going to fall someplace else. So it is effectively removed from the immediate place it has been used. And it may end up being rain in the Sudan, but it's not going to be rain in this water basin. Okay. So that is one of the big issues. How do we try to minimize the consumptive losses to be most efficient? Okay.
Sir,
yes.
can you explain again the percentages in red? Because when I try to add them up, they don't add up to 100.
Oh, no, that means 60% of the water used for irrigation.
Oh.
So it'd be 60% of 65% in essence.
Okay.
Okay. Down here is a quarter, but a very little. So it's kind of high, but we don't use much for domestic. Okay, so thank you. Okay, Texas and California use more water withdrawn, and in particular groundwater, than any other state. In fact, here we are, Texas and California. It varies a lot regionally, as you might expect. It varies in part by population, but here's the interesting thing. Population has been increasing since 1950, but the green line, which is total water use, has actually been stable or decreasing since about 1980. So that's the good news. The per capita consumption of water is decreasing, and that ranges everything from your share of manufacturing to your watering the lawn. So the good news is we're being more water efficient. But the other thing that's interesting is that a big chunk of that is largely due to groundwater. If you plot the increase and decrease in groundwater as opposed to surface water is staying about the same. So we're being most efficient in our use of groundwater. Okay. Now, we mentioned problems with using groundwater earlier when we talked about groundwater induced or groundwater withdrawal inducing subsidence. So here we have just the San Jose Mercury News this year talking about the result of groundwater subsidence. Land is sinking and the homeowners are seeing the domestic wells go dry because the larger agricultural companies are lowering the water table. So these are all big issues. And one of the problems is that California is in a drought. And so it is a drought perhaps of historic proportion. California in the past, in the thousands of years, has had droughts lasting hundreds of years. So here we've got a plot of groundwater losses or dropping over from 1962 to 1913. And even though there's been a couple of little wet periods that have allowed that groundwater to rise, groundwater is just dropping and dropping and dropping. And that is inducing a dewatering of the overlying clays. This particular one is in the San Joaquin Valley. And the dewatering of those clays is resulting in compression of the layer and lowering of the ground. So this is a problem we've talked about earlier, and the reason why we continue to talk about it is because when we talk about using groundwater for all of its uses, we've got to think of the environmental consequences, and subsidence is one of them. This is the subsidence rate in feet per year is up to a foot a year in some of the areas locally. Okay, and it clearly can't go on. Okay. The state of Texas, like most states in the nation, have been trying to figure out what is the future of water supply and regional water planning for some time. Every 5 years, the state of Texas comes out with a water plan, and so the most recent is 2012. And so the first thing they've got to do, not a surprise, is to look at the projection in population. That's pretty impressive. We're still growing at one of the largest rates of population increase in the United States. And so that will be a demand on everything, from space to air quality to water supply, etc. Okay. Now, if you look at how the water presently is being used, okay, that is to say groundwater, how groundwater is being used in Texas, about 80% is being used for agriculture, almost all of which is irrigation. About 15% for municipal and 5% for industries. Okay. Now, what's interesting about that is the projections, because we're trying to project to 2050, and this particular is going to be projected to 59%, and this is going to be to 31%. So the projection is that the total amount of groundwater that we're going to use is going to be almost cut in half, from 57% to 31%. And that the bulk of that is going to come from irrigation. So what we're saying is that we're going to, as a state, be using irrigation a lot less. Okay. In fact, here is how the energy demand is projected. Municipal is going to rise more or less with population. On the other hand, irrigation is going to have to drop, and we're going to have to be increasingly efficient in things like manufacturing, electric, etc. And by the time we're down here, we don't project any increase. Okay. Well, this has a lot of implications as to the economy of Texas, where we're going to be putting our money. And if you live in the Panhandle or West Texas, areas that are very much influenced by irrigation, or if you're a rice farmer, these are important graphs because it has to do with the availability of water, because we're increasingly, the demand is exceeding the supply. Okay. This is the demand and this is the supply. Okay, so we got to figure out how to make those two meet. Okay. Okay. Well, we know about the hydrologic cycle. We've talked about here. That portion of the rain in our case, that falls and doesn't run off as surface water, but rather infiltrates into the ground and has the potential for recharging the groundwater. Okay. So that water that comes down has several things happen to it. Like here's the precipitation. Okay. Some of it is evaporated. We know that. Some of it goes into the soil zone, but then is picked up by plants, and it is lost by transpiration. Transpiration is the process by which plants release water. Now, in reality, it's very hard because evaporation also occurs on plants. So we tend to lump all this together as evapotranspiration. So that is a loss that goes back into the atmosphere. Okay. Now, the vegetation doesn't consider it a loss, but it means it doesn't recharge the water table. Then basically it drains through the unsaturated or veinous zone until it hits the saturated zone, and below the saturated zone itself is basically the phreatic zone. So phreatic is the $10 word for saturated, veinous is the $9 word for unsaturated. Okay. Now it turns out the water table, which is where we think of as being the top of the water that's freestanding, is actually not quite the same as the top of the saturated surface, because capillarity tends to pull water up a little higher than the water table. So the water table, if you dug a hole right here, that's where the water would be. That's the level to which water would rise in a hole or a well. The capillary fringe is also saturated, and the height of that capillary fringe depends on the permeability and grain size of the individual fragments. But we're going to kind of ignore the capillary fringe. Okay. So what a water well does is basically you drill a pipe. You want to have a watertight casing so you don't have any leakage, both from coming up and also from areas that you drilled through, because you only want to be tapping water from a particular interval, and that's going to be basically where you have a slotted pipe that flows in, and then the water comes up, and there's a packing seal, and it's a simple equivalent of a oil or gas well. Okay. The key is we want to isolate it from upper zones. We don't want to have any leakage as we bring it up. Okay. Isolate because the upper zones may be contaminated. In fact, the upper zones are often contaminated. Okay. Well, when we look at this zone here, here's the slotted pipe. Here's the level to which the water rises. That's the level in the pipe, and that's our water table. If you look at the grains that are in the unsaturated zone, you'll see there's spaces. There's spaces because it's drained, but you'll also notice there's still some water in the veinous zone. Okay. That water is being held by capillary forces. Even though it's not saturated, there's still enough capillarity, rather surface tension, that there's a little fringe of water. Now that's really important because that's the water that the plants use. Because as that water drains, if it drained entirely, then plants would have to come all the way down to the water table to get their water. And there are some plants that do that. Some plants have very long tap roots, and they actually can take advantage of the water table, but most plants don't. So most plants, there's a zone, and I just call it the soil zone. That's not exactly a good term, but just think of it as a zone that's equivalent to the depth to which the roots will go. And that's a zone where you can actually get water out of here. So they'll actually be sucking water out that is attached until they can't get it anymore, and then they die. And that's actually called permanent wilting. Okay. So we could think of 100% saturation or something less unsaturated but not affected by plants, or something even less where the plants have sucked it dry. So all of these are changes in the amount of water with different levels. Okay. Now the porosity is the first thing that we want to know, because that tells us the volume of water that could be stored in a particular stratigraphic horizon. So that's basically the percent void space. In this case it's 30%. And so we could have up to 30% by volume of water, or oil or gas. Certainly the issues that we deal with groundwater are very similar to the issues we deal with petroleum. Okay. Now, if we started with saturated water and we let it drain, which is how it goes, when you wet it, when it rains, it becomes temporarily saturated, and then that water soaks down. Now remember, we talked about that. When the surface water is saturated, what happens to infiltration? It slows down or stops. What happens then? There's more runoff. Okay, so we know that the top can be saturated because we know that affects runoff, but that saturated zone will slowly drain. Okay, so what you get out by draining, more specifically by gravity, is called the specific yield. So that's how much water you can get out, what part of the porosity, if you like, you can get out by draining. Okay, and what's left, that's the specific retention. Okay, so after draining, what's left is specific retention. So not a surprise, if we looked at porosity, that's going to be equal to the specific retention plus the specific yield. Okay, so that's how much you're going to have. Okay. Now, the specific yield is different than permanent wilting, because that specific yield is just that's can't drain by gravity. Plants can suck out more. Okay, but if we ignore plants, then this is how much we have that we can get out. Think of specific yield as being the effective what can be drained by gravity, and so therefore can be collected in a well. Okay. Now, if you look at porosity, specific yield, and specific retention, these two will always equal this. Okay. The highest porosity is about 55%, and that's in a well aerated soil. And notice the specific yield is 40. So most of that will drain out. Okay. Now, the next highest porosity is clay. What, 50% is water, but look at the specific yield. Almost nothing. The specific retention of clay is very high because that water is trapped between the little house of cards like plates that we have from those clay minerals. Okay. On the other hand, look at sand. Sand, 25%. Not nearly as good as soil, but look at that. 22% of that drains out. Okay. Sandstone, on the other hand, first of all, it only has about half the porosity. So we got to ask ourselves, why does it have less? And only about half of that can come out on draining. So what this is telling us is there's a lot of variability with respect to the lithology, both in terms of porosity and how much of that saturated material can actually drain by gravity. Okay. Now, the water table is basically the level to which water will rise in an unconfined aquifer. Now, what it basically is a measure of potential energy. So remember we talked about the Bernoulli equation where we used streams and we said that the surface of the water is a measure of potential energy. But then we had another part to that. We had a kind of an invisible line that was the total head, the total energy. And that was proportional. That was a measure of the kinetic energy and proportional to the square of the velocity. Well, kinetic energy, or that velocity head we sometimes call it, is negligible with groundwater. It just moves too slow. So when we talk about the head available for groundwater, it's basically the potential energy. Okay. Now, because the elevation of the groundwater varies, so too does the head, and variations in the head or elevation of, in this case, the water table, is basically the driving force for causing groundwater to move. And in this case, actually in all cases, it's moving from higher energy to lower energy. Okay? And in this case, it's moving from higher energy on the flanks of the stream and then being discharged in the stream itself. Okay, so the stream is basically the discharge area, and the area above the water table is going to be the recharge area. So water comes in by rain and feeds the stream. And so that particular flow, that is generated by the return of the groundwater is called what? What kind of flow? A surface flow is that? Think of your hydrograph. It's that portion of the water fed by groundwater.
The base flow.
Base flow, exactly. Yeah, so base flow is just basically that water that took a roundabout way to get into the stream. Okay. So here we've got that soil water zone, the unsaturated zone, and the water table, and these lines are actually flow lines. Okay, so they're basically tracing the direction that the water is moving. It comes down here, works its way through here. Remember, some of it, though, comes through here. We talked about that through flow because of the difference in permeability. Okay, so the same concepts we talked about with respect to surface water are useful to know with respect to groundwater. Okay, so here's that case where the water table adjacent to the river is higher than the river, so it is a gaining river. It gains water, or is effluent. And then if the water table is lower than the river is actually the recharge zone, and so it is a losing river. It loses water as it sinks into the ground. So that's going to be an ephemeral river where big rain comes, water comes down, and then it just soaks into the water and it's dry for the non-rain years. Okay? A perennial river is going to be one that always has water in it, and frankly, it's not always raining, and so during those times when it's not surface water, it's base flow. Now, we could contour the water table just like we contour the surface of the land, the topographic contour. Okay? So those are lines of equal elevation. But in this case, a contour line is lines of equal elevation of the water table. Now, lines of equal elevation are lines of equal energy. So we can think of this as an energy map, with the highest energy being here, highest head, lowest energy here. Okay. So water will flow at right angles to those contours. We can, because it's always going to take the steepest route down that energy gradient. Okay. So here the water is just coming down like this. But here the water table is verging. It's making a V. And notice the water table is lower in the river than if you were to extrapolate that line over the river. So that tells me that the water table is dropping to the river. So it's got to be a gaining river. Okay. Here, the water table is actually lower than the river. Okay. And so the river is actually feeding the water table. Okay. It's the losing river. So the first thing I want you to kind of keep in mind is that when you contour the water table, you can draw lines perpendicular to the water table, and those are the stream flow lines, if you like. Those are the lines that tell you the direction water table is going. Why, or direction the groundwater, rather, is going. Why would that be of interest? Why would you even want to know what direction the groundwater is going? If it were polluted, would you want to know? Yeah, I would. Yeah, there are all sorts of reasons. And so think about that question as we go on. Why do we do this? Okay, and short answer is for a lot of reasons.
I have a question.
Yeah.
About the previous line. You said that the water table contour line was also a line of equal energy.
Yes, equal potential energy.
Equal potential energy. So what's the depth that is taken into consideration? Is it like from the surface to the water table, or from like the diagram?
Well, in most cases, it'll always be at or below the surface. At the surface where the stream is. If we go back, notice every place there is an unsaturated zone. Everywhere here the water table is below the surface. The only place when the water table is at the surface, and I'm talking about water table now, not anything else, would be where a swamp or the actual surface of the stream. Okay, so water table by definition can't be above the surface. On the other hand, the piezometric surface or potentiometric surface of a confined aquifer could be above, and we'll mention that later. But it's always going to be below the surface. Does that answer your question, or did you have something else in mind?
Well, I was trying to understand like how the potential energy came into place into like the contour lines, because potential energy is basically mgh depending on that's like basically, so the h is like the depth of the height. So that's what I was trying to figure out. Like,
Well, one of the things you could do, imagine if you were to contour this surface or contour this surface. Okay? If you contoured that surface, it would get low. There would be a trough where the stream is. And the elevation of that surface would be the stream. If you contoured the surface here, it's going to be a hump. And the elevation could be as high as the stream. And so when you contour that, here it's a hump, and here it's a trough. And so that's telling me that in this case, it's draining into the stream, and in this case, the stream is actually feeding the groundwater table. Okay? Okay. So let's take that unconfined surface, this water that's saturated, and we're going to pump it. And when you pump it, there's a certain amount of water that's withdrawn, and it forms what we call a cone of depression. Okay? So it decreases in elevation logarithmically, and of course radially, hence the cone analogy. Okay? And so the water that we get is basically the specific yield from this volume. So if you knew the volume of the cone of depression, and if you knew the specific yield, then you could predict how much water you pumped. Okay? Because that's where the water comes from. It comes from dewatering the water saturated zone, the Leo zone, by gravity. We're letting gravity force that water into the well. Now, the problem is, the more water you pump out, the bigger the cone of depression. And so here are a couple of little users, maybe a little cone of depression here. They're not pumping much water out, and so that cone of depression is a low volume. And now in comes your neighbor, who is Del Monte Foods, and so they start pumping, and that cone of depression is much deeper and much wider. And of course what that does is it causes the neighbor's small wells to go dry. So just as lowering the water table by decreasing recharge, that is droughts, can cause shallow wells to go dry, one big user can cause adjacent users for their water tables to go dry too, because of the relative size and aerial distribution of that cone of depression. Okay. Now, one of the problems we have in Texas, or rather this area of Texas, we have rice farmers. And the rice farmers rely on surface water as much as they can, but there's a lot of constraints to who can use the surface water in Texas. And so much, if not most, of the water that the rice farmers use is for irrigation through pumps from wells. Okay. Now here, there's going to be a new 150-foot, there's going to be a new well that rice farmers are going to use more and more of. Is causing the county wells, the city wells, to go dry. So we literally have a case where these are the rice farmers and this is the city well. Okay. And needless to say, you have a conflict as to who owns the water, who controls the water use, is it fair, is it legal? And so those are important questions. And it turns out the question of who owns the groundwater kind of depends. There is an English rule that basically says, I own it, I can do whatever I want with it, and the heck with you. Okay. There is an American rule which is applied in areas where there's limited water supplies that has to do with reasonable use. Okay. So you try, and not a surprise, this is mainly in the western part of the United States. That's the dry part. Where are we more likely to use groundwater? Where it doesn't rain a lot. Okay. And so in those areas, you're more likely to have a conflict. So you try to limit the water use to reasonable and beneficiary. People are going to argue, what is that? What it is supplying the water to the river more beneficial than for crops. And so part of what you're trying to do is develop a safe yield, which is basically some kind of an equilibrium balance between the water table and the rates of withdrawal and whatever needs to go into the river. Okay. In Texas, which is we're always a little strange, we range from being really dry to really wet. So you could argue that we should, in the eastern part of the Texas, use the English rule and the western for the western rule, but instead we use something that's more based on the English rule. And we actually call it the law of the biggest pump. And so basically it says that whoever has the biggest pump can pump the most water. And so that is essentially a version of the English rule. And then once you pump it out, you can sell it, and it's all yours, even if it came from beneath your neighbor's land. Okay. And so the only way to limit the use is basically to develop conservation districts, which is more along the line of what we think of with the American rule, where you have to decide about beneficial uses. Okay. And so as we'll see, that's more of a Central and West Texas issue. Okay. Now, there's one other thing you might know. We think of rivers, particularly in humid areas, as areas where groundwater flows into the river. But you might know, look what's happening here. We've got a well, and it's near a river, and we start pumping. Okay, and of course we start getting this cone of depression. And that cone of depression expands as you dewater more and more water. But here, that cone of depression has intersected the river. That's kind of neat, because that means you have an almost unlimited supply. You are literally draining the river. And obviously the porosity of the river is 100%. So you got a lot more water here than you're going to get from here. So that's what we call induced stream recharge, and that can be beneficial or a problem. It could take polluted water from a river and bring it in. On the other hand, it could increase the rate at which you can pump water. On the other hand, it could decrease the amount of water that's available in the river. So this is one of those things you would look for when you begin to think about the consequences of this expanding cone of depression. Okay. Now, this, of course, is one of the reasons why we want to know the direction of water flowing. Here we have the direction, and here we have a waste site that is polluting the water. And so what's happening is that we've got a plume that's moving with the water, contaminated water. Now that plume gets larger and gets more diffuse, but depending on the nature of the pollutant, it could still be contaminated until we hit the river. And then, of course, what we hope for is dilution. But we need to know that. Of course, if you've got a well here, well, then you're really screwed, because you're pumping now that polluted plume. If you have a well here, you don't care. That's your neighbor's problem. Okay. So the understanding of where the water is flowing and understanding how water quality varies with that flow of water is one of the main goals of the groundwater hydrologist. So let's take this example here. This is something bad. Maybe it's an old chemical waste dump, and you have a well right here. Okay. Now it turns out you have information on the depth of the water table when it's not being pumped. That's the important thing. Not being pumped. And so what you're going to do, you're going to contour that water table. Okay, so now we got 140 feet, 150, 130. Okay, so now you have to decide, am I worried about that particular area? And the first thing you would do is draw lines at right angles, and you say, well, nope, not my problem. Now, but the other thing you have to remember is that there's a diffusion, and so you'd want to know, okay, well, still not my problem. Okay, things look good until you start pumping. Okay, and the reason for that is that if you have a cone of depression here, what's that going to do to the shape of that water table? It's going to create this cone of depression. And what does that do? It changes the direction of the flow of water. Okay. So in this case, you're inducing a recharge to your well from a contaminated plume. Okay, now there's another thing you need to know, and that is the speed. How fast does the water flow? Now, there's a couple of reasons for that. But one of it is that allows you to predict how far that plume may have gone. If you know, for example, when that material was dumped, and you know the velocity, then you can kind of figure out, okay, how much area has been contaminated. It's kind of a first cut on that, okay? And so here we want to know how fast. Well, it turns out that for much of the area, it's years. It can, if you're real close to a river, it can be flowing through in days, but much of the river, much of the water in the overlying unconfined area migrates at rates on the order of years. Now, it turns out that there are aquifers below these confining layers. In fact, we have aquifer confining layer, aquifer confining layer. We'll talk more about that in a moment. But there's some water that seeps down here, and quite literally it can be hundreds or thousands of years old. So depending on the geologic history, now in this case, as well as the hydrologic history, we can be pumping really old water, and that's in fact what we're doing in the Panhandle. We're pumping water that's 10,000 years old, 18,000 years old. Okay, so let's go back to that question. How fast is it moving? Well, it's going to be moving proportional to the slope of the energy gradient. Okay, and so we can think of that as the change in head or change in potential energy with respect to distance. Okay, so that's going to be a delta head, delta L. Okay, oops. Yeah, and that's the head difference of delta L. Okay, so that's the slope, and we're going to use that as one of the primary variables in determining, actually initially the velocity, which is K times S, and the discharge, which is velocity times cross-sectional area. Okay, so if we want to know the discharge of water, it's K times S times A. If we want to know the velocity of water, it's K times S. Okay, so K is a constant proportionality. The velocity of water is proportional to the slope of the energy gradient. But what is that constant proportionality? It is the hydraulic conductivity. Okay, and we think of that like we do permeability. That is, how easy is it to for a fluid to flow through an aquifer. But I'm going to make a distinction in just a moment between hydraulic conductivity and permeability. Hydraulic conductivity is restricted to water, and that's what we're interested in now. Okay, so Darcy's law also can be expressed here, where it's just the velocity. Now that is the Darcian velocity. It's not the actual velocity. The actual velocity has to take into account porosity. Okay, because when you look at that water that's flowing through, it's not flowing through a pipe. It's kind of working through a lot of little channels. And so that slows down the velocity, and it slows it down proportional to the porosity. And so, or inversely proportional rather. The larger the porosity, the faster it flows. Okay. The smaller the porosity, the smaller the holes, the slower it's going to go. So if we want to know the velocity of water, okay, this is flowing through a permeable fluid, or a porous fluid, better said. This is what we want to know, where this is hydraulic conductivity, this is porosity, and this is the slope of the energy gradient, which so far is just going to be the water table. Okay. Again, this is why it flows more slowly, because it doesn't have a direct path. It's got to work its way around these little tortuous pathways, and so it's going to arrive later. It just can't flow as fast. Okay. Okay. Now, I did this as an exercise and I forgot the answer. So, well, that's the answer. You've got a 30% porosity, a slope of 1 to 1,000. You've got a hydraulic conductivity of 1.2 times 10 to the minus 3. It's going 4 times 10 to the minus 6. That's like 0.00004 meters per second. That's really slow. Okay, it's about 2 meters a year. So the flow of water, depending on the slope and the porosity and the hot conductivity, is very slow. Okay. While we're at it, compare this equation to Manning's equation. Where Manning's equation, V is proportional to slope, inversely proportional to the roughness, and that constant of proportionality is the hydraulic radius. So both of these are equations that we use to determine the rate of flow. One for surface water, or the velocity of flow, and from that the rate. One for surface water and one for groundwater. Okay. Now we kind of have the good news that because it's very slow, on the order of often centimeters per day, the previous one was unusually slow. That means that if it's polluted, it doesn't go very far very fast. So if you pollute groundwater, it's not like a river where the pollution could go downstream in days. But the bad news is that it is slow to recharge. So if you're trying to pump it out, that's a limit to how fast it will pump out as well. So you can't pump it out at rates like you can a river either. Okay, and you can't clean it up like you can a river. It's much slower to clean. Okay, so these are three words that are really important to know because they're properties of reservoirs, and these words could apply towards oil reservoirs, gas reservoirs, or aquifers. Porosity we've talked about. That determines how much water you might hold. Permeability is a measure of the material. It's a characteristic of the material through which a fluid is flowing. It is an intrinsic property, independent of fluid. Okay. Hydraulic conductivity is the permeability with respect to water. Okay. Now, if you're a groundwater hydrologist, you're interested in hydraulic conductivity. If you're a petroleum engineer or petroleum geologist, you're interested in permeability because you're going to want to know what are the properties of the fluid that is flowing. And it could be heavy oil, it could be light oil, it could be gas, it could be any number of things. And so it's much more variable. So you want a number that is intrinsic to the material, and then you can vary what kind of fluid you think is coming through. Okay, so we're going to ignore permeability, although I may refer to it periodically by mistake. And what you think of as permeability for groundwater is hydraulic conductivity. Okay, so here are some numbers, and this is in meters per day. Look at this, 4 times 10 to the minus 3 for granite, 4 times 10 to the minus 2 for clay, 200 for gravel. So there's huge variation, orders of magnitude variation with respect to that constant of proportionality for the rate at which water will flow for a given slope, of the energy gradient. Okay. Now this is a logarithmic scale from 10 to the minus 14 to 1 meter per second. And look at the variability. We got 3 orders of variability, 3 orders of magnitude of variability. We got almost 4 orders here. And of course we have high to low. So there's a lot of information in something like this. Okay. But one of the things I would point out is look at sandstone versus sand, and look at limestone versus karst limestone. Okay, so even the same, or something that would seem kind of similar, has a lot of variation. So let's look at that. This is just some more of the same. Let's look at what's controlling that porosity, and then subsequently that hydraulic conductivity. Let's start with intergranular porosity that's associated with, let's say, grains of sand or particles in general. Okay. That would be the primary porosity. That is what happens upon deposition. When you deposit sand or mud, there's a certain amount of water that's trapped in it. Okay, that is the most it's going to have until something else happens. In fact, it's going to get less with time. As we'll see, it's going to be less for any given material due to things like compaction and cementation. But it's also less at the time of deposition. For example, a poorly sorted sand will have less intergranular pore space, less porosity than a well-sorted sand. But now comes the good news. From the point of time that a sediment or a rock is formed, as it is buried, heated, it tends to lose that primary porosity. But at some point, you can begin to get secondary porosity. Maybe we fracture the rock, and so we've got fractured porosity. Maybe we dissolve the rock. That same dissolution that causes subsidence in carbonates and evaporites is causing holes in our granite and resulting in increased porosity. And the extent to which that porosity is interconnected, it's increasing the hydraulic conductivity. Hence, the hydraulic conductivity of karstified limestone can be 4 orders of magnitude higher than limestone that was just deposited without any particles between. So we can make a list. Easy exam question. Porosity is a function of what variable? Let's see. Okay. Sorting, shape, packing, cementation, fracture, dissolution. Okay. So we're going to look at those geologic features and see how they affect the total amount of fluid that a particle that could be contained in that material. So look at sorting first. I've already mentioned it. Well-sorted material versus poorly sorted material. You're going to have more porosity with well-sorted material. The poorly sorted material basically fills in those voids. So the more poorly sorted, the lower the porosity. The primary porosity depends in part on how those individual particles are stuck together. Now, in the case of clay, it's high primary porosity because those individual clay particles, as they settle, give you this house of cards effect. Crystals of granite grow together, and so there's almost no primary porosity in a crystalline rock. Okay. So we've got low porosity. And this is just the analogy of marbles and sand. You're better than that. Okay, so what happens with that primary porosity of clay when you compact it? Well, basically, you squeeze out the water at a high specific yield. Okay, eventually, takes a long time though, that's the problem. It doesn't come out as gravity. Actually, specific yield's the wrong term because it's not water that's coming out because of gravity. It's water that's coming out because of compaction. Okay. And a lot of water will come out of clays with compaction upon burial. So that means there's a lot of reduction in volume. And what is this? Well, this is subsidence. Okay. Clay, on the other hand, sand, you're rearranging the packing order. You might go from a cubic to a more compact or dense sorting, but basically they're round, and so you can't reduce the volume much by increasing the packing order. Now you can significantly reduce the volume of pore space by cementation. And of course, compaction and cementation typically go on together as we are burying sediment. So by cementation, we can lose some or all of the porosity. Here we have a calcite cemented quartz sand. it had a lot of primary porosity, but all that primary porosity is gone because of the cementation of the calcite. Now the interesting thing about that, we've lost all of our primary porosity, but calcite can be dissolved. And so maybe if you're lucky, as you bury and heat that calcite cemented quartz sand, you might dissolve it and generate some secondary porosity. That would be great. But suppose that was quartz cement. So we had quartz cemented sand, and then we buried it. Quartz doesn't dissolve. And so once you lose your primary porosity due to quartz cementation, it's all over. You will never regain that primary porosity by dissolution. Not of the cement, anyway. Okay. We also have what we call fracture porosity. This really should have said porosity here. If you break something, then you create places to store water in the cracks. It's not huge, but it beats zero, and it can locally be pretty significant. And that would be the same thing with shale as it is with granite, where an unfractured shale, because of compaction, will have some porosity, but virtually no permeability or conductivity. But when you break it up, you increase both porosity and the permeability. And that is, of course, the whole rationale of hydrofracking of your shales to get, in this case, not the water out, but the oil or gas. Permeability, again, I'm going to use that term in a general sense as opposed to water. Here we have clays that are compacted, low permeability, small pores. Here we have loosely cemented gravels, high permeability, large pores. So you have both large pores and permeability. Now here's a case, fractured granite, high permeability, but low porosity. A porous pumice or scoria, it's got high porosity but low permeability. So it's not enough to have water, it's got to be interconnected. So you need those pores to be interconnected somehow. Okay. Now here's a trick question. What about size? Which of these two, the gravel or the sand, would have a higher permeability?
Gravel.
Gravel, because it's easier to go through a big hole than a little one. Which of these would have a higher porosity, the gravel or the sand?
The gravel.
The gravel? Okay. How many people think it's the gravel? How many people think it's the sand? How many people think it's the same? Okay, well, let's see. I cheated a little because this is simply an enlargement of this. And porosity is a percent. It's a percent void space. So the percentage of porosity hasn't changed. The size of the pores has. The percentage of the porosity determines the the percentage of the pore space determines the porosity. The size of the pore space helps to determine the permeability. Okay. So this whole time I've been talking about something that I've assumed we all have a shared knowledge of, and that is aquifers. And an aquifer is a saturated rock or sediment that's capable of transmitting significant quantities of water under ordinary hydraulic gradients. Okay. I've actually done a few caveats because sometimes you think, oh, it's a rock that has water in it or saturated water. No, you've got to be able to get it out. And if you can't get it out, it's not an aquifer. Or if you can't get it out fast enough, it's not an aquifer. Now, how fast is fast? Well, it kind of depends on what the use is. If you're just a little rural cabin, you don't need to get the water out very fast. So you could have, as your aquifer, providing your domestic water, something that's got a relatively low hydraulic conductivity. On the other hand, if you are the city of Houston or wherever, you need a large volume. That little piddling amount that'll keep that cabin going is not nearly enough. So you would have to have a much higher hydraulic conductivity to be an aquifer. So an aquifer is defined in part on how it's going to be used. Okay, and normal hydraulic gradients, well, you don't want to have something that, you have to apply so much suction, literally not allow gravity, that, but rather pull it out to create a very steep gradient. You don't want that. So you want something you can generate by gravity drive. Okay. So what do you want? You want high porosity and high hydraulic conductivity. That's what you want. And how high and how hydraulic just depends on the need. So this is kind of a checklist of relative characteristics. Well-sorted gravel has the very highest porosity and hydraulic conductivity. The porosity of a well-sorted sand is the same, but the conductivity is a little lower because smaller grains. Poorly sorted will be lower than well-sorted. A well-sorted sandstone is still going to be lower than a well-sorted sand because of cementation and compaction. A fractured shale would have low porosity, but it could have high hydraulic conductivity because those fractures are linked, and so the water can get going pretty quickly. And finally, limestone ranges from low to high. And I'm going to leave it at that and then ask you next time, why is there such a range in porosity and hydraulic conductivity of limestone? And I've already told you the answer, but think about it. So I will see you next time.